Hi, can you hear me? I noticed that you were inside the Discord, so I joined in here as well.
Yeah, I just had to mute your YouTube. I had both open.
Sure, that's fine. Let me just quickly modify this a little bit. I will join in to the Discord with my laptop as well in order to screen share with low latency. But yeah, I took a look at the problems and should be able to go through them in pretty quick order.
Yep.
Any in particular?
I was able to do 10 out of the 13.
Okay. Sounds good.
It was the first session, right? So I didn't really know, like if I'm supposed to just finish everything and then just show up.
Mm-hmm.
Right, so I just looked at the question. If I could solve them right away, I did them. And if it took like a bit of thinking, I just left them for the session.
Sure, okay. Do you want to start with the problems that you thought were a little bit tougher?
Yeah, so...
By the way, we're streaming right now, so it's going to be, recorded and all that.
Yeah.
Okay.
So the first problem that I was kind of struggling with was the question 6.
Question 6. Ah, yes. This one was kind of interesting. So, by the way, can you see my screen?
Yeah.
Okay. Yeah, so this problem took me, well, no, I saw this one. This one kind of harkens back to a problem from last semester. Do you remember that problem, I think, on the very first homework set of the last semester, where it was sort of like, given that a function is continuous and there's one point that's non-zero, right? Yeah. There was some point that's like f of a not equal to 0. Prove that it's non-zero on an entire interval. Do you remember that?
Okay, yeah. Yep.
Yeah, this is extremely relevant because, okay, so first of all, I'll give the intuition and then I'll wrap it up in sort of the language of contradiction, right? Like, what if this problem did not have the guarantee that G was continuous, right? If you didn't have the guarantee that G was continuous, then you could have a situation where, like, it looks like 0, 0, 0 most of the time, and then there's sort of like just a point-wise discontinuity, and then it goes back to being 0, right? And the issue with this is that if this was your function, let's call this f of t, so this one is not continuous. You could have a situation where the integral of f of t, and I'll do absolute values dt, is equal to 0. Even though f of t itself is not the 0 function. Right? But the fact that g of t is continuous guarantees us that this can't happen. Because if you tried to, if it's continuous, if a single point is 0, then everything around it, or a little bit around it, has also got to be non-zero. Which means that the integral will come out positive. There'll be some area under the curve. You see that?
Okay.
So basically, this way, either the integral of g of t dt is equal to 0, or how should I word this? Or g of t is non-zero somewhere. And this is an exclusive or. It's saying exactly one or the other of these must be true, right? It's saying either, this is basically saying it's 0 everywhere, or it's non-zero somewhere, at least somewhere, because you have the guarantee that it's continuous. You see what I'm saying?
Yeah, that bit makes sense.
Yeah. So, okay, that's sort of the intuition, right? But this is not a rigorous proof, and I think this is expecting you to talk a little bit rigorously. But the proof goes pretty similarly to whatever you did last semester, where because this value is, let's give it some value, let's call it like C or something. But because this value is non-zero, and because it's continuous, that means there's got to be like some interval that's entirely above C over 2. You see what I mean?
Yep. Yeah.
And then based on comparison to a rectangle of, I guess the width is probably going to be some, what was it? For every epsilon, there exists a delta, right? By the definition of continuity, you're guaranteed a rectangle of width delta and height C over 2. And C over 2 times delta is some non-zero area, right? So basically, doing it this way, you can show that if there was one non-zero point, then you would be guaranteed some C over 2 times delta area, which would contradict this thing being 0, right?
But like in contradiction proof, right? Like
Yeah.
the proof by contradiction, aren't we supposed to like assume that?
Yeah, so let me just give a really brief rundown of what a contradiction proof is, because it's kind of one of your first time seeing it, I assume. Is that a fair assumption?
I don't know if you lagged out or I lagged out.
Oh yeah, it seemed a bit choppy, but I'm just asking, is this one of the first times you've seen contradiction? It's lagging again.
I did do 1019, which is like proofs.
Sure.
Let me.
But okay, maybe just as a quick reminder, right? The idea of a contradiction proof.
4G, 5G, I didn't get that much.
What's up?
I was just gonna switch my network band.
Sure. Okay. Well, just the very brief idea behind a contradiction proof is, you start out with a couple of like axioms, right? And let's say that there's some like claim A that we know is good, right? And there's some claim B that we know is good, and maybe some other claims too that are good. And then we have one claim in particular, let's call it claim like Z, that's like kind of suspicious, right? Now the idea here is if you assume that all the good, let's just assume for sake of contradiction, it's basically for sake of contradiction. All right, let's assume Z is true. And the idea is using all these things together, if we use only, 100%, correct logic, using all these things together, put them together in some way using steps that are verifiably correct, some logical sequence, and we get to some absurd premise. If we can get to some absurd premise, like, if we can get to some statement that's like P and not P for any P, really, if we can get to anything absurd at all, and we know that this is perfect and these are perfect, then the only thing that must be, wrong was Z in the first place. That's the idea, right? That's the idea behind contradiction. So let's talk about the language of this problem. This problem is basically asking us, blah, 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 as well as use a proof by contradiction. So basically we're saying, suppose G is continuous. Okay, that's like one of the things we're assuming, are bulletproof, right? G is continuous. And what is it? And that's this thing, and that the integral of this thing is 0, right? The integral of the absolute value of G is 0. And we want to show that, the claim that's going to be suspicious is going to be G of T is a 0 function. And we basically reword this by saying G of T is non-zero somewhere, right? This is the claim that we make for the sake of contradiction that will turn out to be BS, but we like to assume that it's true at first because it gives us something to work with, right? The fact that we assume it's non-zero somewhere means that we can suddenly talk about this structure, right? It suddenly gives us, between this and the continuity, this lets us start talking about some finite area under the curve that lets us contradict this thing. Make sense?
Yeah, that makes perfect sense.
Okay, that's awesome. So far, so good, I hope. So far, so good. Yeah, okay, what's the next one? By the way, I think we had someone else joining us as well in the Discord. Feel free to...
2 others joined.
Okay, sure. Yeah. I think they have already left, but yeah, okay. Anyways, this is being recorded and all, so you can always refer back to it. But what's the next issue? What's the next thing of interest?
So the next one is the next problem, 7.
Yeah, one of these was really poorly worded. Suppose f and g are two different continuous functions. Prove f and g cannot have the same average value. This has got to be some just really choppy wording, because like...
Yeah, I was thinking a similar thing, because with ranges, right? Because no range is given.
Yeah, exactly. Okay. I think it's saying that prove... I think it's essentially saying prove there must exist some range where f and g don't have the same average value. I think that's what it's saying. Because like...
So like we can just pick any range?
Or this is sort of like that for every and there exists, right? The claim... or sorry, right? So it's like prove that there exists some range. Oh, I think this is what it's asking you to do, over which f average is not equal to g average. I guess it's saying for every f comma g that are continuous with f not being completely equal to g. So given prove, okay? Given f and g are both continuous, but they're not equal to each other, prove there exists some range over which the average is different. Like, I think that's what it must be saying, because the question is so absurdly vague that, like, you know, I think we basically got to make some assumption here. Like, honestly, if I was you, I would probably try to ask the professor really quick to see if they can clarify the wording, because this wording is junk. Right?
So we choose whichever range we choose is the same for f and g, right?
Yeah, that's the idea.
Yeah, because if it's different, then
so like prove there exists some range, like a to b, over which the averages are different. And do you have an idea of how you would do this? I think you can reuse the previous part by quite a bit.
I thought about this question.
Uh-huh.
And so I just thought of a simple, like, let's say from 0 to 1 as the domain, right? And I thought of x and negative x as functions, right? F and g.
Yeah.
And something like, I don't know, without even doing any math, it just tells me that their average must be the same. Like if you just say x and then negative x, let's say plus 1.
Okay. But those have different averages, right?
I didn't do the math for this one. I was just like thinking about it in my head.
One of the things is you don't get to choose nice functions. You can a little bit as intuition, but all that you're told is, you know, basically for every f and g, right? So all that you really know is that f and g differ. There exists. So the fact that f and g are continuous but not equal to each other means that there exists some x where there exists some x where f and g have a different values, right? And because they're continuous, this means that you also know a little bit in their neighborhood as well. You see what I mean? Like, the fact that they're not equal, basically there exists some x where f of x is not equal to g of x. Which means that the same, in fact, there must be a little neighborhood around x on which they are not equal because of continuity. And the way to see this is maybe just to find h of x is equal to f of x minus g of x. And the fact that f of x is not equal to g of x means that h of x is not equal to 0. And then the problem starts to look a lot like problem 6, the one we just did, right?
Yeah.
Yeah. So the fact that they're not equal on one point means that h of x is not equal to 0 at that point, but also on a little neighborhood, right? So if we graph this, this looks like h of x must be non-zero. And from there, so they would have the same average value if the average value of h of x is 0. So you basically just got to prove that the average value of h of x is not 0 over some range, right?
Okay, so so since f and g can be any function, right, for all functions.
Yes.
Right. I feel like, so I just want to go back to the same like equation that I had before, right? Like x and negative x plus 1.
Sure.
If you do the subtraction, if you subtract one from the other, I think you get 0 as a function. Like if you do x minus 1 and then x plus 1. I mean negative x plus 1.
Sorry, I'm a little bit confused. I'm not sure that there's any value in talking about a specific x or negative x here. Sorry, are you talking about like specific functions, x and x plus 1?
Yeah, so like a function like x plus 1 and negative x minus 1.
Okay, I'll entertain this for a bit, but where are you going with this? I'm skeptical that this can lead anywhere productive by talking about specific functions.
I think that so I think there's a counterexample to that hx thing, right? So by this example that you gave, right, you're saying that h at x is going to be a non-zero at some point.
Yeah.
I think those two functions subtracted, right? Both of them are continuous.
X and negative x plus 1?
I think x minus 1 and then negative x plus 1.
Negative x plus 1. Okay, so one's the negative of the other, right?
Yeah.
And you think this is a counterexample to what I'm saying about h of x?
Yeah, I think it just gives you 0.
No, it gives you taking f of x, you're subtracting them, not adding them, right? So f of x minus g of x turns into 2x plus 2. 2x minus 2, not 0. Right? Because this is x minus 1. And this is, well, they intersect at one point, maybe?
Oh, I see.
But they're totally different on most areas.
I was adding the two functions.
Yeah.
Okay, yeah. Now, yeah, they have to be the same.
So the problem, once you reduce it to this point, it's pretty darn similar to problem 6. The idea is, it's not completely identical because we're not talking about absolute values, but the idea is we're trying to come up with a situation where the average value of h of x is greater than 0. Right? And that would prove that f and g would not have the same average value on that interval. So basically we just need to find, it's very similar, right? The fact, let's just say that this h of x takes some value c, just look at c over 2, right? And by continuity, we're guaranteed that there's some delta interval where the function has at least value c over 2 everywhere in that delta interval, which would guarantee that this value, the area under the curve, is at least c over 2 delta. So the average value is at least c over 2. You see what I mean?
Yeah.
Yeah. So yeah, that should be totally sufficient.
Yeah, that's good.
Yeah, good so far. Okay.
Yep. So the next one, I didn't do question number 10.
10. Okay. Gotcha. I'm curious. Did you get question 13?
So I did get a solution, and
Yeah.
I just like made up my own examples, and I checked my solution, and it seemed to work. It seems to work.
Did you assume constant acceleration and a constant force?
Yeah, I did assume constant acceleration and constant force.
Yeah, the question is pretty ambiguous about it. And if you do assume constant acceleration, the problem becomes very easy. Because then you can just use a kinematic equation from basic physics. It's a little bit harder if you don't assume constant force and acceleration. And the answer turns out to be the same, but the proof is quite different. And based on the wording of their problem, it seems to me like they want you to do it using the calculus way, which is non-constant acceleration. But yeah, we could talk about that later. You said problem 10, right?
Yeah, it seemed a bit too easy, 13.
Yeah. Okay, we can talk about that after. But you said problem 10, right? X is equal to fy?
Yeah.
Is a continuous positive function for y is an element of 0 to 100. Okay, so I'm just going to draw out something, right? X is equal to fy. Oh, I don't know. That maybe looks something like continuous positive function. I guess if this is x and this is y, I don't know. Maybe it looks something like that. And it's rotated around x is equal to 0. So it's rotated around this axis, right?
Yeah.
So now it looks kind of like a Beyblade or a dreidel or something. Okay, now it forms a container. So y is equal to 0 is the bottom, and y is equal to 100 is the top. And so are you reasonably comfortable with shell integration or disk integration at this point? Some students in Calculus 2 starting out really struggle with the concept, and I just wanted to sort of ask where we're at with that.
I'm totally fine with shell
Uh-huh.
and with the washer method.
Okay, that disk and washer are pretty much the same thing.
Yeah.
Yeah, so y is the bottom of the container, y is 100. Suppose the container is filled with water to height h, okay? So some height h less than 100. Using the washer method, find the volume of the water. Okay, so just as maybe a quick review for anyone that happens to be watching, the way to do this is basically to express... so h and y are kind of our... how do we put it? We basically want to look at an arbitrary disk or an arbitrary washer, right? Which is kind of like a very short cylinder. So this cylinder is basically going to have some cross-sectional area. Area is equal to pi x squared, right? Because the radius of this circle is just going to be x. And area of a circle is pi x squared, which is equal to pi f of y squared. Because x is equal to f of y, right? I'll write it like this. And the idea here is our little sort of like differential disk has height dy. So if we want to integrate to get the volume, right? Like total volume is equal to the integral of every single like differential volume added together. This basically becomes dA, or maybe let's start it like this. This basically becomes area times dy, where area is just equal to pi x squared, or alternatively pi f of y squared dy. So this is a quick explanation of the justification behind the washer method, or disk method, or whatever. So, okay, that's the volume of the water, right? And if the water evaporates at a rate proportional, okay, so this is pretty standard, but the hard part of this problem is if the water evaporates at a rate proportional to the area of the surface of the water, find the rate at which the height of the water changes with respect to time. Okay, so let's figure out how to write this. This is basically saying water evaporates at a rate proportional to the area of the surface of the water, which is basically area, right? So that's saying, I think that's saying dv dt is equal to the negative of some constant k times area. Is that right?
Yeah, it looks right.
Water evaporates at a rate proportional to the area of the surface of the water. And the negative sign is because it's evaporating rather than being added. The k is just to represent that we're told that it's proportional, but we don't know the constant of proportionality, so we're leaving that as k. And then it's, okay, proportional to the area of the surface of the water. Okay, great. And this area in particular has got to be some function of h, because whatever the surface area is depends on how high it is at that moment, right? Which obviously I just said it depends on h. So that's basically equal to pi h squared, if I'm not mistaken. So this is minus k pi h squared. So far, so good? Seem okay?
Yeah.
And now it's asking us find the rate at which the height of the water changes with respect to time. So this is basically asking us to find dh dt. So WTF means want to find. dh dt, this is what our answer is. And I think the idea here is basically we need to use chain rule to break up dv dt equals dv dh times dh dt. And just bringing this right down, this is equal to minus k pi h squared. So we want to solve for dh dt, which basically means we got to figure out what dv dh is. Seem reasonable?
Yeah.
Yeah. Do we actually know what dv dh is? Well, h is basically the same thing as y, right?
Yeah.
H and y are basically the same darn variable. So what's the rate of change of this volume with respect to h? So okay, at this point, if we can find dv dh, we are done. And we said that v was equal to the integral of pi f of y squared dy, right? Gosh, I hope I'm doing this right, but this goes from 0 to h. So if we do, we basically just got to take the derivative of this thing, right? So this just basically becomes, are you following? 0 to h pi f of y squared dy. And to me, this looks like just a nice, neat little application of one of the fundamental theorem of calculus. I forget which form, but right, the idea is if you're taking the derivative of an integral, they kind of just cancel right out and leave you with just a perfectly nice expression. So maybe you can, I hope with this kind of like explanation, you can maybe solve the rest yourself. Feeling okay about that?
Yeah, I was just struggling more with just the wording of the question at the end a bit.
The question at the end?
The part at the end, I was just struggling with what it meant.
As part of your solution, denote t as time, v as the volume of the water, and the proportionality constant is k. And summarize colloquially in a short paragraph what the washer method is. That's what you mean?
No, you already explained about, right? The as well if water evaporates.
Oh, gotcha. So you were just sort of confused about this part?
Right. Yeah, you explained about that.
Okay, so you feel pretty good about it now?
Yeah. Now it's good.
Okay, that's awesome. Glad to help, and hope you and your friends can sort out the rest on your own. Oh, by the way, I should ask, how big is the class?
The class, so basically we don't really have like a class Discord. It's like a bunch of classes merged together Discord.
Interesting.
It's not just one class Discord. So it's like hard to gauge at like the actual size of the class.
Oh, gotcha. Yeah, that's too bad.
But I know like a few people who like continued from last semester.
Gotcha. Are most of you CS majors, math majors?
Most people I know are CS majors.
Gotcha. And some just like the first class enough to want to go forward?
I guess.
Okay. Are you in that boat yourself?
I was more like I chose both my courses in like September, and then I just like was too lazy to switch it out, so I just stuck with it.
Ah, classic.
And plus, I did like decently well in the first one, so I just.
That's good. Like, what was your thinking for the first one overall? Like, I think I was told that 400 people started and like 200 or 300 dropped after homework 1, despite me helping as much as I could.
Homework that was the case. Really, like, it was a huge struggle. But like after that, it got easier, definitely.
Yeah, no, I definitely think that they had some heavy weed out from the first one. And by the way, for the person joining us, we're just talking through some problems. I am recording and streaming it right now because that's how I did things last semester. So just, be aware, right?
I've been watching the YouTube stream. That's why I jumped in.
Oh, great. But yeah, I think we were getting to sort of discussion on question 13, maybe, unless there are any other.
I just wanted to quickly discuss like one bit of question 13.
Yeah, what's 12. Up? 12. Okay, what's up?
So I solved the question 12. So basically, I didn't know if it was like an actual, like an absolute value function, right? So I calculate the slope of one line. I calculate the slope of the other line.
Yeah.
Right. They come out to be the same thing.
Yeah, right? But like negative, right? So what is this? Y is equal to rad 3x, I think. Because this point is a over 2, root 3 over 2a. And this is a, and this is 0, right? So this is y is equal to rad 3 minus rad 3x, I think. Sound good so far?
Let me just get... I got, for the second one, I got... Yeah, that's exactly what I got, yeah.
Good, okay. So far, so good.
I think it's a rad 3 minus x rad 3. So there's an a in the front.
There should be. You're saying there should be an a in here.
Equal to a square root of 3 minus square root of 3x.
Let me think about that. This should be the only a. This should be the only a, right?
Yeah.
Right, because the slope is just regular root 3 and negative root 3. But the intercept should have the a information. That's right.
Yep.
Okay, so far so good. Okay, what's up about...
Okay, so then
Mhm.
I went on to solve the area, like for the whole like rotated half cone, right?
Rotated. Okay.
So like you rotated, it's a double cone. So like so I integrated from 0 to a over 2, and then from a over 2 to a.
Yes, because this halfway point is sort of where it changes, right? So that sounds reasonable.
Right.
Yep.
So in my mind, it seems like they both should be the same. So like from 0 to a over 2 should be the same as from a over 2 to a.
Like volume-wise, the contribution to the volume when you... So like, drawing this thing out, this is sort of like a weird little cake-looking thing, I guess. Right? This is kind of what it looks like.
The best... Oh, I think it's rotated over y equals 0. So the x-axis.
It's rotated over... Wait, didn't I draw... This is rotated over x is equal to 0, right? So that's this line right here.
Oh, yeah.
So I think I drew it correctly. So it looks... I don't know. Kind of looks like a volcano, for lack of better analogy. Volcano. Yeah?
Yeah.
But let me guess what you're trying to ask. You're basically saying, hey, I wanted to like calculate the volume contribution from like this part, right? And maybe you just wanted to double it to get the volume for this part as well.
Yeah.
And you notice that this didn't work.
Yeah, exactly.
Very good question. Very reasonable question too. Let me use an even simpler shape. Let's say instead of this triangular thing, let's say I was just integrating like maybe a block like this, okay? Maybe a block like this. And I'm still rotating it about that axis, so now it looks, kind of like a volcano, but instead of like a triangular base, now it's like a I don't know what to call it. It's not a volcano anymore. It's more like a armband or something. I don't know. But if you applied that same logic here without the like strange triangular shape to throw you off anymore, would you say that the volume up to like the halfway radius is equal to the volume of the outside part?
No.
Why not? I agree with you. Why not?
Now it becomes obvious.
Now it becomes obvious. Very good. Very good. That's exactly what I was hoping to point out by just using this this picture. But to just voice it out for maybe anyone watching, the idea is that if you sort of do this halfway point, right? It's sort of like it has a smaller radius, so to speak. So there's not going to be as much volume, right? Like this part here isn't going to contribute as much as the outer layer just because it's sort of like further away, right? Because, if the... How do you put it? It's because this thing is sort of expanding. As the radius expands, the contribution is sort of pi r squared, right? Because the base is sort of a circle. Which is saying, like, if you draw this out even further, right? The further out you go, the more area or volume is being added with each subsequent extra extension to the radius. Hopefully that makes it clear enough. And the exact same is going on here. It's just drawn as a triangle instead of a rectangle, which might make it a little bit harder to see. But yeah, I hope that clarifies everything.
Yeah, that's good.
Okay, that's awesome. All right, so for the last one, yeah, let's figure out a way to do this with calculus. So how did you do this one? If not with, if you felt like it was too easy?
I assumed, because it said if force F acts on an object, I just assumed F was constant.
Yeah. So like, I did it that way at first. I dislike how ambiguous it is. I just like how ambiguous it is, but this whether or not you assume it's going to be constant, the answer is going to be the same either way. Because it kind of has to be, right? If there was some like way to do this with integral for a general f, so f general, not necessarily constant, like for the case where a specific case of general is constant, right? So they still kind of have to agree. You know what I mean? But that's not a very good way to prove it. So let me start by showing you how I would do this with constant, and let's see if we kind of agree. But if f is constant, this basically turns into a kinematics problem, right?
Yep.
And if we just have the equation from kinematics, that's sort of like saying vb squared minus va squared is equal to 2a times whatever the change in s is, right? So then if work is equal to integral of force dot ds, and because we're assuming force is constant, this is just basically f times the change in s. You basically just divide through by 2a, and then plug that in over here, right? So this turns into f work is equal to f times vb squared minus va squared over 2a, and then f is just equal to ma, so the a's cancel out.
Yeah.
Is that basically what you did?
Yeah, exactly the same.
Yeah, exactly the same. Okay, gotcha. So it's just based on how they're saying it. Use Newton's second law of motion and a substitution rule to find t as the time, s of t as the position, v of t as the velocity, w as the work. To me, it sounds like they're asking us to do this via calculus. And I actually had to think about this a little bit because I was wondering to myself, if this equation is always true, even if a isn't constant. And it turns out it is. Which I think is very funny. So now let's talk about the general case where we're going to do this with calculus. So we're doing the same thing. W is equal to f of t. You know, I'm just writing it as f of t now to indicate that we're not making the assumption that it's constant, dotted with ds. And the idea is basically we want to substitute both of these things in terms of, well, in terms of something that'll get us closer to what we want, right? In terms of velocities, basically. So f of t is equal to ma of t, which is equal to m times dv dt. So this wasn't too bad, right? This was basically just rewriting acceleration will let us express, rewriting acceleration as velocity will let us express f in terms of velocity because, well, f and a are almost the same thing, right? They just differ by a constant.
Yep.
But now the kind of issue is ds, right? What are we going to do with this ds? So ds over dt is equal to vt, right? This is just change in position with respect to time as velocity, right? Pretty simple.
Yep.
But let's just rewrite it like ds is equal to vt dt. Now this is sort of notationally kind of silly, but this is how we do it with integration, right? When we talk about integrating a little differential piece, this is just the differential notation.
Yeah.
I've always thought of this as being not very rigorous, but I mean, it works. You know, if you're a physicist, this is fine. So the idea is, okay, well, let's just go ahead and plug this in, right? Let's plug in this value for ds, and let's plug in this value for dt. So this gets us integral of m dv dt times v of t times dt. Now, depending on how barbaric you want to be, this is basically just canceling dt with dt. It's chain rule, basically.
Yeah.
So this turns into m times v of t times dv. Oh, and we should mention that this was at sort of position A rather than acceleration, right? A to B. So I'll write position A. It sucks because acceleration and A use the same value here. But now it's going to be v at A to, it's going to be v at A to v at B. And at this point, we don't even need to think of velocity as a function of t anymore, because now we're just integrating with respect to v directly. So this just becomes the simplest integral in the world, mv squared over 2, I guess. And maybe you can just finish it off from there without giving the whole thing away. But you should be able to verify that it comes out to be exactly the same as your specific case where acceleration is constant. But this problem, I think, is just a neat little exercise in chain rule that actually took me a good 15 minutes to think about. Being a little bit rusty in calculus, sometimes my chain rule gets kind of weak. Here's the thing about chain rule. It's very hard for me to actually see what's going on with chain rule. I usually find myself just chasing notation down. You know what I mean?
Yeah.
Yeah, like I can't physically picture what's happening here when I mash these two things together. I'm basically just chasing down notation. But that seems to work at the level of, well, that never stopped working for me.
Yeah, I do the same.
Yeah, like it's weird because I learned chain rule in calculus, but I felt like I really didn't start like I wouldn't even go as far as mastery. I felt like I didn't really have a good handle of it. Like I only started knowing how to like use it deftly once I got to like an upper level thermodynamics course in physics. Right? We just had the most simple expressions, like literally just canceling, doing some chain rule canceling, and it just blew my mind because like physically I couldn't understand it, but it just somehow always worked. And maybe I have something to answer for if I ever do go back to school. I probably need to brush up a little bit on my fundamentals a little bit. But nevertheless, this should be, I think, reasonably rigorous, at least at the level of this class explanation of what you ought to be looking for. Like, I'm pretty sure this follows the hint of, like, substitution, right? Yeah, substitution rule. Yeah. It's, you could almost think of this as like you could almost think of this S and V as a sort of U substitution almost, where S is equal to VA plus the integral of, I guess this would be T equals 0 to T of VU du, where U is just some dummy variable. And then taking ddt of everything here, you basically just use fundamental theorem of calculus, which kills the VA, and then just basically just turns this into a VT. Right? But my point here is basically when you do U sub all the time, you do U is equal to like, I don't know, like x squared plus 1 or something, and du becomes 2x dx. The exact same thing is happening here. It's just a S ds pair. Right?
Yeah.
Yeah. So this is like, it always kind of bothered me that this is how I learned, or everybody learns U substitution and basic substitution tricks. Because
I just think everyone does the same thing.
Yeah, like everyone does it this way, but like I've never really gone and thought deeply about whether or not this notation is actually rigorous or not. Because if you see DUs floating around in the air when you're doing differentiation, usually somebody complains. But people don't seem to complain when it's integration. And I've never actually thought deeply about why that is. Maybe it's just everyone agrees that to not complain about it, but anyways. But you see the problem, what's basically happening here is U substitution. It's just written in a, like, it's just a little bit hard to see because nobody likes writing S this way, right?
Yeah.
But really, this is what's happening. I think. Anyways, feeling okay about that? Feeling like we pretty much handled that?
Good. Yeah,
alrighty.
Everything is good.
Okie dokie. Yeah, I think I will end the stream right there unless there are any other questions we'd like to address. I think everything else was mostly straightforward integration or something like that.
Yeah, it was pretty easy.
Yeah, someone else was asking about number 2, I believe, using a fundamental theorem of calculus, which I'll just quickly address. But if h of x is equal to 0x x squared f of t dt, the idea here is you can basically pull the x squared out because it's constant with respect to the integral, which is only in t. Right, so this is basically x squared, integral from 0 to x, f of t dt. So now they're basically asking us, okay, then what is h prime of x? So if you basically think of this as one piece and this as one piece, this turns into a product rule situation, right? Where, okay, the derivative of x squared, we all know this, right? And then the derivative of this other piece is just going to be an application of fundamental theorem of calculus. So hopefully that makes everything clear to the student who was asking about it. By the way, would you know how to take the integral of something that looked like, I don't know, x cubed up here? Do you know what to do in this situation?
No idea, no.
Yeah, this one pops up a couple of times. But the way to do this is basically to let u be equal to x cubed. So then this just becomes sort of du. Then the idea is that d dx is equal to d du dx, and du dx is just equal to 3x squared. So this d dx operation is basically like saying, okay, this is the operator that gets applied to this integral, and then du dx is just this extra 3x squared that's just hanging about from the chain rule. So this is equal to d du of 0 to u f of t dt. And then you just, and then this just gets multiplied by 3x squared. I think, yeah. And then at that point,
Yeah.
What's up?
Yeah, I was just saying, yeah, I've never just seen these kind of problem, right, where you have like x cubed in like
Yeah.
the integral bit.
But like it could really be anything up here, right? Excuse me. It could really be like anything like, you know, square root of x or x squared or what have you. But the idea is basically the same. And then once you have fu times 3x squared, at this point you just substitute. So you end up with like fx cubed, 3x squared. And then it's like, oh, look, wait a minute. This is basically just what my usual chain rule looks like, right? It's like if the original problem was taking d dx of x cubed times this thing, right? It's almost like this is the part that comes from the fundamental theorem of calculus, and this is the part that just pops out from chain rule. Right? So it's very elegant. I agree. I don't see this very often, and when I saw it for the first time in a couple of years, I had to remind myself a little bit about what to do. But that's the idea. Yeah, so I think with that said, I will end the stream there, unless there are any last questions.
No,
Okay.
that's it.